analysis 1A lecture, I'm not sure, it's possibly 21. And we are back from spring break, and we will now be going over a bajillion prompts of homework and then learning some new things. Ready to go? Yeah. Okay, let's do it. First of all, there's even a plan. We are going to go over the optimization homework. I gave you, can you kick out the door? I gave you 3 optimization prompts for homework, 40, 54, and 59. Which ones would you like to go over? We probably can do like 1.
54.
Wait, 40 or
40, 59. 59. 54.
Let's take a vote. Who wants to do 40? 1, 2 persons, 3 persons. Who wants to do 54? More than that. Who wants to do 39?
59.
Okay, good. 59. Looks like we're doing 54. Sorry. So 54 is this problem all about, it's like laying pipe or some crap like that, right? Okay, we begin. Extremely efficient class day we're having, Ethan. Let's start. Number 54 says, an offshore oil well is 2 kilometers off the coast. The refinery is 4 kilometers down the coast. Laying pipe in the ocean is twice as expensive as on land. What path should the pipe follow in order to minimize the cost? Okay, so it's like this. There is a shoreline. Can I have your attention? There's a shoreline, and there is an offshore oil well. In other words, we discover oil somewhere, and the place where we discovered it is 2 kilometers off the coast. So this is the coastline. This is water, and this is land. All right. The refinery, the place where the oil is processed, is 4 kilometers down the coast from this point. And so this was the general idea here. That the refinery is 4 kilometers down the coast from the closest point of the oil well itself. All right, now we would like to this is all about just getting the oil to the refinery in the most efficient way possible. Now, and we're going to have some pipe, which is going to be sending the oil from here to here. Now, common sense initially might suggest that we should try to get there in as short a distance as possible. And that would involve going straight from the oil well to the refinery. So that seems like a thing. But it is perhaps more difficult and annoying to have pipe going underwater because there's like things to worry about, leaks, pressure, sharks. Exactly.
What?
Whereas on the land, it might be easier. And in fact, the problem says that every kilometer of pipe which is in the water costs twice as much as every kilometer which is on the land. This is called a minimum path problem, and this is actually one of those, some of you may have thought as you were doing this problem, like, wow, calculus is actually really interesting and useful for solving like real problems. This is like a real thing to do. So, if the cost of the pipes is the same, then that would suggest that I should go straight for the point. If the cost per kilometer of the pipe in the water is way, 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 way more than the cost per kilometer of pipe on land, then I should probably just go straight to the shore and then go over. Everybody with me? Okay, and so do you feel the sort of tension in the problem between going directly and having the minimum distance versus having the minimum water distance? Everyone just nod if you're kind of like with the problem. All right. So it might turn out that the actual path that we should take follows some kind of middle ground. And so all of this sort of thinking was necessary to understand the problem. So this blue line represents the, can you take that paper to Schwartz? He left it here again, he does it all the time. I think that's it, right?
This is hard, so turn it on, give us some.
This blue line represents the path that we're taking, and so now I have to start deciding, like, I have to find out what that minimum path is. So I have to pick some variables. What seems like a good variable to pick? Yes?
You could call x the side of that triangle.
Yeah. Let's just pick a variable. There's no particular reason which one of these but it just seems to be a good idea to let this be x. If you let this be x, it also works, but it just kind of ends up to be like a more annoying algebra problem. Well, if this is x, then this is the square root of x squared plus 4, and then this is 4 minus x. So I think if you got this far, I think you did the hard part, or almost. Understanding the problem, drawing a picture. They did not provide you a picture for this problem, and coming up with, you have to have the confidence to come up with your own variables to represent the situation. Okay, and now what we want to do is we want to minimize the cost. So we need to construct a cost function. So what is the cost as a function of x? Yes?
2 root x squared plus 4 minus x.
Yeah, that's basically it. So what he is essentially doing is just saying, well, look, the actual prices are irrelevant. All that really matters is that this is twice as much. So you're sort of saying, like, well, let's just call this like $1 per kilometer, and let's just call this $2 per kilometer. Is everyone okay with that? If you want to be more fancy, you could pick some constant like k or something to refer to the price of this per kilometer, and then this would be 2k per kilometer. Then it'll just have this free-floating k factor, which just does nothing and just sits there and just has no effect on the problem. You guys okay with this? Kind of like rambling, but I think it makes sense. Okay, so if we take Calvin's suggestion, we just let this be $1 per kilometer, and this $2 per kilometer, then the cost of sending the pipe from here to here and here to here will just be, the cost of the pipe in the water plus the cost of the pipe on land. And the cost of the pipe in the water will be the distance the pipe goes in the water times the cost per kilometer. So that's 2 root x squared plus 4 plus 4 minus x. And now, raise your hand if you got this far. Okay, uh-oh, that's not that many people. Those of you who didn't get this far, what happened? Raymond, talk to me.
I didn't understand the problem.
You didn't understand the problem.
I
Yeah.
didn't draw the picture.
At all? You didn't even attempt to draw a picture?
No,
Oh, you drew the wrong picture. Okay, yeah. I think that what makes these problems hard is that they're real world problems you have to read, you have to understand, you have to think, some level of common sense required, like experience in the oil industry. Routinely rated the #1 earning petroleum engineer, tops every list that they publish. Does anyone know what I'm talking about? Like in Forbes every year, they're like best possible careers for the money. It's like petroleum engineer 1, and all the way at the bottom is like social worker. Yes?
It's a pretty crappy job.
It's a pretty, well, it's...
It like pays very well.
Yeah, it pays very well. All right, so, nonetheless, what? Math teacher somewhere like, I don't know. So, now that we have constructed a cost function, the problem becomes kind of easy. It's just a matter we can turn off our brains for a minute and just do some calculus. I would like to, the whole goal of this problem is to minimize the cost. Thus, I need to minimize this function, and I can use calculus to figure out where this function is minimum. So let's just like quickly do that. I'll rewrite this as 2x squared plus 4 to the 1/2 plus 4 minus x. Now I will differentiate with respect to x. That's going to be zoom zoom, x squared plus 4 to the negative 1/2 back inside 2x. Derivative of 4 is 0 minus 1. And this is my derivative. This is kind of a little awkward. Well, I'll write it one more time. This is just 2x over root x squared plus 4 minus 1. And I guess I would like to know when this is 0. So I'm going to kind of skip all that factoring crap and just kind of like set it equal to 0 and solve, because that seems like the thing to do. So if I set this equal to 0, I end up with the equation 2x equals root x squared plus 4. Did I do that right? Yes. If I square both sides, I get 4x squared is x squared plus 4, and thus we have that x is the square root of 4/3. Is that right? No. Yes. Yeah. Square root of 4/3. So did you get 2 root 3 over 3 for x?
Yes.
Yeah. So there you go. The conclusion of the problem is that the most cost-efficient way of getting the oil to the refinery is to head for a point on the shoreline, which is 2 root 3 over 3 away from the closest point on the shore. Follow? Okay, good. Do you want me to like do a 1-minute cram of one of the other two problems, like 40 or 59? We might have time for that.
59 might as well. 40?
Okay, just like really, really fast. I'll start 40. 40 says there is a hemisphere. There is a tank in the shape of a cylinder plus 2 hemispheres, and the total volume of the figure is 3,000 cubic foot per something. No, just 3,000 cubic feet. And what we need to do is we need to cover the surface of this spaceship with solar panels, and they naturally cost more for the curvy bits than they do for the less curvy, only in one dimension bits. That seems reasonable, right? You with me? Yeah. So the part of the surface area covering the spherical parts are twice as much. So this is actually similar to the other thing. And so what I know is that the volume of this thing is 4/3 pi r cubed plus pi r squared h, where I am letting r be the radius and h be the height. And if I set this equal to 3,000, I now have a relationship between r and h. And the surface area of this thing is going to be, well, it depends on what the different parts are, but what's relevant to me is what the cost is. And the cost is going to be, well, again, let's do the Calvin thing and just say, let's just say that the solar cells on the lateral area of the cylinder are $1 per square foot, and then the solar panels on the curvy bits of the spherical part are $2 per square foot. And thus, it's sort of like, you might think of it as almost as if there's twice as much surface area to cover on the spherical parts. So then that becomes the surface area of the sphere is 4 pi r squared, so it's just like 8 pi r squared, and then the surface area of this part is 2 pi r h. And so to finish this problem off, all you do, again, raise your hand. For those of you who had trouble with this problem, did you not even get this far? Or you did get this far and couldn't finish it? I'm wondering where the problems are. Is it the reading comprehension and modeling, or is it the calculus? Someone speak up for those. Laura.
I got that far. At the very end, I think I got an arithmetic error.
Okay. Yeah, so essentially, but everyone knows what you have to do here, right? You take this equation, you solve for h, right?
Yeah.
And then you stick it in here, and then you have constructed a function in terms of a single variable r, which gives you the cost, and then you minimize the cost function with respect to the r variable by differentiating and blah, 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 blah.
But the answer
I think you end up with r, as I just did this problem last period, it was even on the board as you were walking in, it was like cube root 1125 over 2 pi, is that right?
Yes.
Oh,
Yes!
I got that right.
Yes.
Yeah.
We were just like the answer's so ugly, so
Yeah,
it
how
must
is
be
that
wrong.
even a real answer?
And then when you tried to find h, it was just
What's up?
I just
I
did.
didn't even try.
Oh, and then Eo, taking it to the next level as usual, plugged it back in and figured out what h was and observed that h is actually 4r.
What?
Thus, the best dimension spaceship would be one in which the height is like 4 times yours. That's kind of cool. Or the height is twice as tall as the
No, I
diameter.
didn't look like it.
All right, it actually makes total sense
It's the top.
because it cuts just twice as much or something. I'm not sure if it makes total sense now. All right, that was optimization. There was also a rectilinear motion packet. How did that go? Yeah, is that a good?
Can we check our answers?
We can check some answers to this.
Oh,
I thought we could do one problem was did you do rectilinear motion packet? Okay, let's turn to page 9. Let's turn to page 9. I thought this was a good problem we got.
We have to write a paragraph.
So yeah, I'm going to talk about that in a second. So I just want to make sure everyone's cool with this. I know it's not that hard, and I know we did it in class, but still. So here we have a position function, t minus 2 squared t minus 4. Step 1 of this problem is to take all derivatives, do all algebra, make sign charts, not mess up. So let's see, taking the derivative of this to get velocity, I think it's actually simpler if you just use the product rule instead of multiplying things out. So it's like derivative of the first would be 2t minus derivative of the first times the second plus the first times the derivative of the second. So that would be t minus 2 squared, and the derivative of t minus 4 is just 1. And then I can factor this, take out the t minus 2, and I am left with 2t minus 8 plus t minus 2. So that is t minus 2, 3t mince 10. Is this what you guys did basically?
Yeah.
Okay. Cool. So that is my velocity function. factored in a nice way. What about my acceleration function? Well, I guess I'll just use the product rule again. Derivative of the first, which is 1, times the second. So 3t minus 10 plus the first times the derivative of the second, which is just 3. And so if I simplify that, I get 6t minus 16, which could also be written as 3t minus 8. All right, so this is another one of those things. Don't drop the baby by taking the derivative wrong or factoring wrong, otherwise everything will be wrong. All right, now that I have the position, velocity, and acceleration functions, the pro way to do this is to make number lines, nice, neat, clear, well-labeled, legible number lines, all right on top of each other in an overlapping fashion. Yeah. So the position function looks like, well, what does it look like? It's a cubic. There's a root at 2, and there is a root at 4. No sign change at 2, however, because this is being squared, right? So it's going to look like this, and behavior like this. Be positive over here and negative here. Is everyone okay with this? I'm going super fast because we're all so awesome. How about the velocity? The velocity is going to change sign at 2 and at 10/3, which is like 3 1/3. It's quadratic, so it'll be plus minus plus, which means I'm moving to the right, then moving to the left, then moving to the right. And then, again, directly underneath for comparison purposes is the sign chart for the acceleration, which is going to change sign once at 8/3, which is whatever that is, 2 and something. What is that? 2 2/3. Cha. There's 8/3, and it's just a line, so it's going to go negative, positive. Okay, awesome. Now come all of these questions in which we ask little follow-ups. Let me just run around and see. Ah! Wrong. Terrible. That's the wrong thing. No. Wait, maybe yes. No, bad. Actually, very bad. What are you talking about? That didn't make any sense. Wait, didn't we do this before break? Who else can I scream at?
Why?
Just those two. No.
Wait, what's wrong?
Okay, guys. Now comes the thinking questions. The thinking questions are, I'll skip all the trivial ones and I'll go right to the important ones. When is the particle moving towards the origin? Part E. I am moving towards the origin when I'm either on the right, going left, or on the left, going right. Thus, whenever position and velocity have opposite sign. And when is that happening? It's happening, we're doing part E now, from negative infinity to 2, and from 10/3 to 4. Right? Those are the places when, Magna, you cool? Okay, and then the other interesting question was part G. When is the particle speeding up? Okay, so Yael and whoever else I screamed at, the particle is speeding up when either its velocity is positive and increasing, or when the velocity is negative and decreasing, right? Because if you're going negative 50 miles per hour and your velocity goes down, it means you're going negative 60. Remember this whole conversation? Yeah. So that means, Arun, that means that I'll be speeding up whenever my acceleration and velocity have the same sign. Good. So when is that happening? That's happening from 10/3 to infinity, and also from 2 to 8/3. Cool? And then when am I slowing down? Everything else. I'm slowing down when either my velocity is positive and decreasing, or negative and increasing, becoming less negative. So that's whenever velocity and acceleration have opposite signs. That's negative infinity to 2 and 8/3 to 10/3. Okay, we cool? Are we cool? Okay, go. All right, the cool problem was the one on the next page. This is so cool, this problem.
Cool to be like.
I think it's cool, and if you don't think it's cool, then you're not cool. That's how that works. All right,
I'm very cool, actually.
Here is what is going to just quickly draw this. This is really barely even calculus. This is essentially a physics problem, but that's what calculus is for anyway, I guess. So we have an interesting thing happens at 2, 190, I believe that is. And then at 8, something happens at, I want to say 10.8 and 12.8. Those appear to be the key numbers. And the time we were down here like negative 90. Boom. And a little bit of like. Okay. And then jump. Okay, that's supposed to be a straight line. Not very straight. So, what is going on? I will read aloud. When a model rocket is launched, can you guys like whisper quieter? When a model rocket is launched, the propellant burns for a few seconds, accelerating the rocket upward. After burnout, the rocket coasts upward for a while and then begins to fall. Shh. A small explosive charge pops out of parachute shortly after the rocket starts downward. The parachute slows the rocket to keep it from breaking when it lands. The graph below shows the velocity data from the flight. Okay, so what I would like to do is to use our sophisticated calculus understanding to analyze this graph and to discuss all of its features. And what I asked you to do, I think, is to go through each interval, and or what I want you to do now at least, go through each interval and explain both the sign, increasing, decreasing, and concavity of the curve on the interval and explain what it means. All right, Magna, let's start. In the interval from 0 to 2, what is the significance of the fact that the velocity is positive?
It means that it's going up.
So, yes, going up, right? Yeah, if here I see that the velocity is positive. So just talking about the fact that it's positive for a moment. If velocity is positive, velocity is defined to be the rate of change of the position. So it's just, if the velocity is positive, it just means the rocket is going up, right? Cool. Yes?
Is it also accelerating in that?
Okay, well I didn't ask that question yet. We're going through one feature at a time. So Calvin, let's do the next one. What is the significance of the fact that the velocity is increasing?
Is getting faster.
Yes. Yeah, it's speeding up, right? If the velocity is increasing, then all we're just saying is that the speed of the rocket is going faster and faster. Or we would say the rocket is accelerating, although I think it's dangerous to start to say something like that, but okay. All right, and so let's talking about the physics of the situation for a moment. Why would the rocket be accelerating?
Because it gets later.
No, no. What does it mean? This was supposed to be not that hard. Are you like chewing?
It's like, yeah.
Okay. What?
I'll just not.
New braces?
I'm so sorry.
It's okay, they'll be off in 6 or 7 years. It'll be fine. All right. Okay, wait, someone else is not mouth crippled. Why is the velocity? The velocity is clearly getting bigger, right? So why would the velocity be getting bigger and bigger? Right? Anyone can answer this question.
Because the rocket is
Okay. What do you got, Ron?
The propellant is burning.
Yeah. Yeah. Can you throw in some more fancy words? The propellant is burning, and thus?
And thus there's a thrust.
Oh. Yeah, there's a force. Yeah, thanks. Yeah, you guys know some things, right? Yeah, Ron says the propellant is burning, thus creating a force, and force is going to accelerate the rocket. So, of course, F equals ma, the rocket is going to go up because you're making it go faster and faster. That's what acceleration is. That's what a force does. Is everyone okay with that? Okay. Now we get to the bonus round. This is a little bit subtle. The bonus round addresses the issue, or addresses why is the velocity concave up on this interval. Now, Rabbi Fleischman.
Because you're using up the fuel, so the rocket's getting lighter.
Yeah, I forgot to make you all pause for a minute and think about it. But yeah, that's the answer. This velocity, as this velocity curve is, we see that this velocity curve is concave up. What's the significance of this curve being concave up? That means that not only is it accelerating, but the speed is increasing faster and faster, right? This is kind of where the calculus is coming into play, right? So it's accelerating at a faster and faster rate. So why would the rocket be going faster and faster? Answer is because as the rocket is going up, it's burning the fuel. And as it burns the fuel, the rocket weighs less and less. And since the force from the rocket is, we think, the same, I guess, assuming depending on the chemistry of it, then since F equals ma, as the mass is getting smaller, the acceleration is getting greater. You guys with me?
Plus, you're also getting like further away from Earth. So
That's like negligible though. That's like really negligible. All right, this stuff is really complicated. Calculating actually how much fuel you need based on the fact that your weight is constantly changing is really hard. It is why they call it rocket science. It's very difficult. And actually, I think that involves that's like a multivariable thing, right? Everyone's not paying attention.
The rocket equation.
Is it like a multivariable thing, or is that just differential equations? It might be just differential equations. Ask Coach to explain rocket science next time you're seeing.
We never touched upon
Never
it.
talked about
I think
that.
it's different Q.
I think it's different Q also. Alright. Okay, awesome. Moving on. What happens at time t equals 2, everybody?
Instantaneous.
Run out of fuel, which is okay if you're a toy rocket, not okay if you're like a plane trying to get to Florida or whatever. All right. So then, please explain what is going on. What is the significance of the fact? Emma, what is the significance of the fact that the velocity is positive on the interval from 2 to 8?
That means that it's still going up, but it's.
Yeah, pause. Still going up, right?
Okay, you know how long it took me to at first I thought that was where it was like.
I know you have to think about it for a while. You have to notice that it's velocity, not position. Yeah. So exactly. Common sense says if the thing is going really, really, really fast and the fuel suddenly burns out, it doesn't just start falling instantly, right? It's not like Looney Tunes or whatever. It's going to keep going up for a while. And in fact, over this entire interval from 2 to 8, what would you say is happening? Yeah, Colin.
It is going up slower and slower.
Yes. So I guess we moved on to the second part of this, right? Which is why is the velocity decreasing? It's decreasing because
The acceleration is
careful. Language is important. The acceleration is what?
constantly Constantly.
No.
I don't.
It's
Constant.
negative, yeah. The acceleration is constant, but it's a constant negative number, right? It's gravity. It's just falling, right? As soon as the rocket fuel burns out, we're in free fall. And what's happening is there is a constant acceleration due to gravity, and that acceleration is causing the rocket to fall because it's just a negative acceleration. And then focusing, in fact, on this entire interval from 2 to 10.8, the rocket's in free fall. The interesting thing is, and what about the concavity? Alice, you have a question, or what about the concavity of this? Kind of a trick question. It doesn't have a concavity. It's a line. Why is it a line? Calvin again. Emma again.
Because the acceleration is constant.
Yeah, because the acceleration due to gravity is constant, or might as well be constant as long as you stay pretty close to the Earth. So that's why this is supposed to be a constant straight line, and the slope of this line is just the constant acceleration due to gravity. Okay, what happens at 8? Someone else. Raymond.
It stops. It stops.
A little bit more.
It was going up,
Uh-huh.
now it's slowing down, and at time equals 8.
Yeah.
Velocity changes from positive to negative.
Yeah.
So it starts going down.
Yeah. At 8 is where the thing hits its peak, right? Keeps slowing and slowing and slowing until it's 0, and now the velocity is negative on the interval from 8 to 10.8. What's going on? Someone else? One of you two? It's going down, right? It's still falling, but now still in quote unquote free fall, but now actually falling down. All right. What happens at 10.8? Okay, what happens at 10.8?
The parachute comes up.
Parachute pops. Alex Coy, not surprisingly, is a toy rocket enthusiast, and he gave us a lecture yesterday in 9th period about precisely how that mechanism is triggered. But never mind that. The parachute pops out. Then what happens? So address, Sandeep, please address the fact that the velocity is negative on the interval from 10.8 to 12.8. What is the significance of that?
It's still going down.
Still going down. Yes, parachutes do not enable you to just go up in the air, right? Okay, so yeah, we are still falling. Who else hasn't talked yet? No, just Sandeep again. Why? Explain the significance of the fact that the velocity is increasing on the interval from 10.8 to 12.8.
When the parachute comes out, the rate at which it's falling is slower. So if it's going down.
Part of this is being able to answer the actual question, not just whatever question you feel like. This is just the significance of the fact that the velocity is increasing.
It's going down.
Oh, actually, maybe what he was saying was fine. I cut him off
Yes,
too
it
soon. Yeah,
is.
take it back. Can you say it again?
So when the parachute comes out, it starts
Yes.
going down slower, and if it's going down slower, it's like our number line is going that way, or it's going towards.
Yeah, the velocity is increasing, the velocity is becoming less negative. In other words, the guy's slowing down, right? The rocket's slowing down, which is what a parachute's supposed to do after all anyway. Okay, now comes the one which is like a little bit difficult to address. Clarissimo, what's going on? What are you doing over there?
I'm like
Picking at your arm. Yeah, what's, explain the significance of the fact that the velocity is concave up on the interval from 10.8 to 12.8.
well, the acceleration.
Concave down, sorry.
Well, the acceleration is negative because the parachute creates like drag or something, or friction or something like that.
Yeah, drag or friction or something like that. Yeah, Buses.
Well, it's concave down because drag depends on speed, so the slower it's going, the less effective drag is at slowing it down.
Oh, real physics just happened. Yeah, that's true. Yeah, we don't even need to necessarily get into the whole reason why this is true exactly, but at least it kind of makes sense, right? But yeah, I guess what he's saying is exactly correct. The parachute opens, and at first, because your speed is so much, the amount by which the amount by which the drag changes your velocity will be higher when the velocity is itself higher, or when the speed is itself higher, yeah. And then over here, it appears that there's some almost like asymptotic behavior that's called like the terminal velocity, right? That's like how like cats can jump off like 100-story buildings, and then they just like.
I don't think it works.
I think it works, right? Maybe
It works on like
20,
50 feet.
50 feet. That's it.
Maybe.
We need to do some experiments. So at some point the guy will just sort of asymptotically be going at a velocity of like -40, whatever it is. Okay, do you guys feel like you get this? This is what calculus is for. Good. Put this packet away. More things to do. There was also some homework. What?
So for E, the answer is
Wait, I love how like we only.
When is the rocket's acceleration greatest? That's a terrible question.
yeah.
I don't know. All right.
I think it's 2.8 because you like it's infinite for a bit, isn't it?
I guess if we're using acceleration in the unsigned way,
But no, 2.8 it's like positive acceleration.
then it would be like here maybe. It
Like, I
appears.
consider multiplication.
It's like right before the 2 seconds.
But also positive infinity. Instantly change.
Yes.
shape.
Yeah, you water.
Yes. Shall we go over this other homework on differentials?
Change shape.
There was a homework on differentials. How'd that go?
Wait, which one was that one? Number 270?
There's like a few problems.
76. So you're going up to speed and you're going another speed that way.
What? Dan will hit you with a book.
No.
Wait.
Yes.
Dangerous.
Like, all the- Look, I
But
just
there
had to, like,
were
get the
some
whole-
problems like 9, 33, 37, 49. Should we do like one of them or something?
49.
Yeah.